So the idea is the following. So there are certain series for which we know. So we know summation n by 1 by n square, n going from 1 to infinity is actually pi square by 6. It is slightly involving to prove that, but nevertheless. But however, if you're given a general series, so you're given an infinite series and you want to make out whether it converges or diverges. So that's the question we have in our mind. We want to basically see how to check if the series is convergent or divergent. So the first thing is to test very quickly for test for divergence. So note the following. So one, here, if limit as n goes to infinity an is not 0, then the series diverges, right? However, if limit as n goes to infinity of an is 0, we can say nothing about the convergence, right? We cannot say anything anything about convergence or divergence, right? About convergence. Yeah, just by looking at it. Of course, you can perform something else and then look at it. Okay, so the other test is basically, so geometric test, we have already know that for geometric test, we have summation a r to the power n equals to say 1 or say 0 to infinity. Then in that case, it converges if absolute value of r is less than 1 and diverges otherwise. Yeah, otherwise diverges. Now, what are the other tests? We have what is called as P series test. So we have summation n equals to 0 to 1 equal to infinity n to the power p converges if p is greater than 1 and diverges if p is less than equal to 1. Then we had example of telescoping series, integral test, comparison test. So in comparison test and limit comparison test, usually compare with P series or with geometric series, usually, all right? Then if it has an alternating sign, then we try alternating series test. And if an is any real number, then you can check for absolute convergence using ratio test or root test. All right. So let's embark on solving the problems. So let's look at the first problem. So when I see a problem like this, my first step generally is to see, okay, is limit as n goes to infinity of an is 0? And if it is not, then it is divergent. All right. So generally, I would not write it down, but I check that all the time. That's the first thing to check in some sense. So for one, we have limit as n goes to infinity of an is limit as n goes to infinity of n sine 1 by n. That is same as limit as n goes to infinity of sine 1 over n divided by 1 over n. Now note that as n goes to infinity, 1 over n goes to 0, and this limit is known to be 1, which is not 0. Therefore, by divergent by divergence test. Now, let's look at problem 2 now. So in this case, there are many tests we can use. We can use comparison test. We can use limit comparison test. We can also use root test to see whether it converges or not. Okay, so let's use any one of them. So let's say, for example, if we use limit comparison test. Okay, so here we have Bn, compare it with what? 1 by 2 to the power n, right? So compare it with 1 by 2 to the power n. And this is your an, right? So this part is your, this is an. All right. So now let's see what is limit as n goes to infinity of an divided by bn. That is going to be limit as n goes to infinity an divided by bn. So an is 1 by 2 n plus sine n divided by bn is basically, you have this guy on top. So first of all, note that they are series with positive terms, all right? Otherwise, you cannot apply the limit comparison test. So what do we get in this case? So this becomes, when you simplify this is going to be limit as n goes to infinity 1 by 2 to the power 1 plus sine n over n. And as n goes to infinity, sine n over n goes to 0. So this is 1 by 2, which is your c, which is greater than 0. Yeah. So therefore we have what? Therefore an and bn both behave alike. Yeah, both converge, or both diverge. However, we know that summation 1 by 2 to the n converges, but this converges. Why is that? Geometric series with r equals to half, which is less than 1. Therefore, we get summation n equals to 1 to infinity 1 upon 2 plus n plus sine n converges. And what is the justification for that? Limit comparison test. Okay, so this is how this problem is done. Now let's look at the next problem here. So we have summation n equals to 2 to infinity minus 1 to the power n, n ln n. So again, here in this case, we can use basically what? We can use the alternating series test to check it. So what is limit? So what is my, this can be written as summation n equals to 2 to infinity minus 1 to the power n bn, with bn is what? With bn equals to 1 upon n ln square root of n. And I would like to simplify that. So that's going to be 1 upon n half ln n, which can be written as 2 upon n ln n. Okay. So bn is this. You can see that, well, you can see that limit as, so things to check. So this is greater than 0. So bn's are positive, right? It should be alternating. So to make sure that it's alternating, bn should be positive, and then minus 1 to the power n makes it alternate. So first thing to check is bn plus 1 less than bn. And the answer is yes. Why is that? Notice the following. You can quickly see that n plus 1 is less than n, and ln of n plus 1 is less than ln of n. If you multiply, both of these are positive. So this gives me, this implies what? This implies if you multiply them out, you'll get ln of n plus 1. So let's just move this here. So then in that case, we multiplied them out. So we get, this implies n plus 1. We get n plus 1 times ln of n plus 1 is greater than n times ln n. And if you take reciprocal of this, you get 1 upon n times n plus 1 times ln of n plus 1. So this means 1 upon n plus 1 times ln n plus 1 is going to be less than 1 upon n ln n, which implies bn plus, you can just use this sign, bn plus 1 is less than equal to bn. So that's 1. And also limit as n goes to infinity of bn is limit as n goes to infinity of 2 upon, so you can multiply this by 2 as well, right? 2 upon n ln n, and that goes to 0. So from 1 and 2 implies series is convergent, and the reason for that is alternating series test. Series. So now let's see. So now let's work through on some of them. So in this case, again, we can use alternating series test or absolute convergence. Both will work in this problem. Yeah. In fact, what about this guy? Again, alternating series test. What about this one? You can also use alternating series test here, or you can use or geometric series, right? This is a geometric series and it converges. In this case, we have to use the only test I think we know is the ratio test. So let's apply the ratio test. Let's do the 4 because it's different than the previous one. So apply ratio test. So limit as n goes to infinity of an plus 1 divided by an absolute value. This is going to be limit as n goes to infinity n plus 1 factorial the whole square times 2 times n plus 1 factorial divided by an is multiplying by the reciprocal, so 2n factorial divided by n factorial square. Now we want to simplify this. So I did not write the absolute value sign because these elements inside are positive anyway. So we get limit as n goes to infinity. N plus 1 factorial square can be written as n plus 1 square n factorial the whole square. 2n factorial. Now this is same as 2n plus 2, so that can be written as 2n plus 2 times 2n plus 1 times 2n factorial. And then we get here, we have n factorial square. So now when we cancel this guy with this guy, this guy with this guy. What are we left out with? We have equals to limit as n goes to infinity, n plus 1 square divided by 2 times n plus 1 times 2n plus 1. If I simplify that further, I get limit as n goes to infinity, n plus 1 divided by 2 times 2n plus 1, which is going to be 1 by 4, which is less than 1. Therefore, by ratio test, this series converges absolutely. Yeah. Now note that what is the problem asking you? The problem is asking you test the convergence. So it converges absolutely, therefore it converges as well. So now if you look at this series is like a telescoping series. Why is that? Let's look at SK. So sequence of partial sum, right? So sequence of partial sum. So if you look at sequence of partial sum, it will be what? The first term is when n is 1, what do you get? You get arctan. When n is 1, you get arctan of 2 minus arctan of 1. So we get arctan of 1. Then what is the next term? So we have arctan of, then the next term will be arctan of 3 minus arctan of 2. So you will have tan inverse of 2 dot dot dot. The last term would be sk, so minus tan inverse of k plus 1 minus arctan of k. Now all these terms will get cancelled. So this term will, this will cancel out with this guy, this will cancel out with next one. So what you'll be left out with is, and this will cancel with the other one. So sk is going to be arctan of k plus 1 minus arctan of 1. So therefore, what is limit as n k goes to infinity of sk? That is going to be limit as k goes to infinity of arctan of k plus 1 minus arctan of 1. Now, as k goes to infinity, arctan goes to pi by 2. And what is arctan of 1? Arctan of 1 is tan inverse of 1 is the same as this guy. So it is pi by 4. So therefore, this series converges to pi by 4. This is an example of a telescoping series. All right, let's move ahead now. What about this guy? So geometric series. Yeah. And what about it? R is what? Here absolute value of R is 3 over pi, which is what? Less than 1. So converges. Yeah, therefore converges. So converges. Now what about this one? Again, you can use what? This also converges, and we can use alternating series test. Now what about this one here? This is a P series. So P series, so converges if P is greater than 1, diverges if P is less than equal to 1. Now comes the question. So which one? So now here's the problem. Now we need to decide already a priori in advance if we want to use comparison test, whether it will converge or diverge. So the way to look at is, look at this part here. Yeah. So this is roughly like 1 by square root of n square, which is roughly like, which is 1 over n, right? So this will diverge. What test can you use? You can use comparison test. How can you use comparison test? You can have 1 upon square root of n square plus 1 is less than 1 by square root of n square. Now here, I cannot use comparison test actually. You see, because I can show that it is less than 1 by n. But what I really want to show that this is greater than 1 by n. So in fact, comparison test won't work really properly. So we should use limit comparison test. So So limit comparison test with, so use limit comparison test. So in limit comparison test with Bn equals to 1 over n. Same thing here as well. When there is too much of noise around here, you should just compare. This is roughly going to be 1 upon what? 2n square to the power 2 by 3, which is going to be 1 by what? 2, forget about 2. This is roughly going to be n to the power 4 by 3. So again, limit comparison test. Note that you can't write like this, okay? This is just for your idea, really. Yeah, when you're writing the solution, you have to write it properly. So limit comparison test with what? With Bn equals to 1 by n to the power 4 over 3. What about this guy? So again, we can use limit comparison test with 2n by 3n summation n equals to 1 to infinity. Yeah, which is a geometric series. All right, few more. So what about this problem? So what are the techniques we can use? We can either use geometric series test. We can also use root or ratio test. In this case, we have to use alternating series test. But before that, notice the following. What is limit as n goes to infinity of minus 1 to the power n by 2 to the power 1 over n? As n goes to infinity, 1 over n goes to what? 0. So this limit does not exist, right? So it's divergent right away. No fancy test needed. Diverges, and the reason is divergent test or divergence test. So note that divergence test applies for all kind of. So you can apply it to any series to check whether it will diverge. Yeah, of course, it doesn't tell us anything about convergence. It will tell you if the series is divergent. No, if limit is not 0, then it tells you that series is divergent. If the limit is 0, then it doesn't tell you anything about the convergence or divergence. What about this one? We can use, so the most reasonable one here to use will be ratio test. Here we can use well, one way to see that is the following. So, well, you should notice that tan inverse of n over n square root of n is greater than or equal to 0, right? What is tan inverse of n? As n goes to infinity, so tan inverse graph is like that. This is an asymptote. The one asymptote is pi by 2. The other one is minus pi by 2. So this is going to be less than or equal to pi by 2 for sure, times 1 by n to the power 3 by 2. Yeah. So you can basically say that now we look at this series. This is a constant multiple of a convergent series. So therefore it's convergent. So you can use comparison test. Right? What about this guy here? So here we can use root test. Yeah, it's not a geometric series, right? Because n is changing as well, right? So root test. What about this one? Again, alternating series test. This one, again, alternating series test. This one here, we can use alternating series test as well. Alternating series test, or you can also use ratio, or you can use ratio test here. Same alternating series test. Here, this is a telescoping, right? So either you can use telescoping, or you can also use comparison test, right? Because after all, 1 upon n into n plus 1 is going to be less than equal to 1 by n square, right? So you can use comparison test. Now, when you look at this series, in this case, first, before you devise your strategy, you should see whether it will converge or not. So this is roughly going to be n to the 4 by n to the power, what? 2 the whole power 3, which is going to be n to the 4, n to the 6. So this is going to converge. So convergent, what test to use? You can use a limit comparison test with bn equals to 1 by n square. Yeah, that's one of the tests you can use. This one, you have to use integral test, right? Again, because you can see that the derivative of ln n is 1 over ln x is 1 over x, which is there. And in this case, because of the factorial being involved, ratio test will work better.